Okay, guys, so we're into the practical side of calculus, the max min unit here. Let me just get my clock open so I can see our time. Okay, so a couple things. Day one and day unit 5 today. We are looking at area problems today. So we're going to look at the practical side. So basically, we're looking at applications of derivatives now. So that means we're going to be using derivatives to solve problems. And one thing that you know with curves and things like that is where the derivative is, the slope is, where the derivative equals 0, you get a max in the curve or a min in the curve. So that means we can find minimum edges and maximum edges of different problems. So we can do max min problems. So the very first thing that we're going to do today is looking at using area and using the derivative with area problems to find max and min areas, mostly maximum areas. Okay. So the first thing we're going to do is we're going to do 3 kinds of examples today, and they're going to deal with area and perimeter. So our first one is simple, and then we've got a couple other ones as well. And so today we'll do area. Tomorrow we'll do number and volume examples. So we'll do maybe 3 examples today, maybe 2 examples tomorrow. And then on the third day, we'll have a practice day or 2 with some practical problems. So if we look at the actual practice in this area, which I'll bring up for you here in a second. Okay, there's a lot of them. There's 5, 9 in here, 10 there, 11, 12, 13, and there's like 20 plus some bonus problems if we don't want. So that's 20 problems. I'm not going to get you to do all of these. So we're going to be doing some problems with area today. So like this, and we'll do problems with volume next day and problems with area. So we're going to do an example exactly kind of like this one here and like this one here today and like this one here today. These 3 are the ones that we're going to do today. Example like this, an example like this, and an example like this. And then we're going to do an example of volume the next day and number, which is like these ones here without the drawings in them. Okay, so let's get that out of our way and do our first example here with the barn example being part of your wall here. Okay, so let's fly this up a little bit. Okay, so a max area problem with perimeter and area. That's the first type that we're looking at. Okay, so a farmer has 1,200 feet of fence wire. He plans on making a pen with the back side being his barn wall. Find the dimensions of the pen to maximize the area. And I probably should have said in there as well, what is the area of the pen? So the first thing in step 1 is we want to derive the area here. Or sorry, not the right area. Draw the diagram of our diagram so that we can see what it looks like. And then we'll take the derivative. So here we have, not a circle. I don't need a circle. Oops. Edit. Undo that circle. Okay, so we need a line here. So here's a barn. Okay, and then he's going to come out with, let's use a different color here, and he's going to make a fence. It's going to come out like this. And he wants this to be his width, and this to be his length, and this is the barn. Okay, so we know in step 1, we're going to write a perimeter equation for the pen. Okay, and the reason we need this is because we have 2 variables here. So this is our width, and this is our length. Okay, in feet. Okay, so perimeter of this is going to be W plus L plus another W. So the perimeter is equal to how much fence he has. So he has 1,200 feet of fence. So 1,200 is going to equal W plus L plus W. So 2 W's plus an L. Okay. Now we want to know how much is the width and how much is the length to maximize this. So in order to maximize this, we have to maximize the area. So then step 2, we want to write an area equation. Write the area equation. Okay, so the area is going to just simply be the length times the width. Okay, so now what we're going to do is we have to maximize the area. Okay, so if we want to maximize the area, let me just shrink this down so that's not sitting up there. My chat there was open. Okay, so we're going to maximize this area now. So in step 3, what we do is we write the perimeter equation in terms of one variable and plug it into the area equation so that the area equation becomes an equation of one variable. So step 3, use the perimeter equation to solve for a variable and write area in terms of one variable. Because we have length and width, right? But we just want. But now, we don't have to worry about which one it is. It can be length or width that we use when we're solving it. It both will give you equivalent results. Okay, when you're solving your problem, so it doesn't matter which one you pick. Okay, so I'm going to pick to solve for L because there's only one L. So let's L. So let's go 1,200 equals 2W plus L. So I'm going to subtract 2W from both sides. Okay, and then I'm going to plug this in to the area equation. So area then equals length is 1,200 minus 2W times the W. Okay, so let's expand that out. Area equals 1,200 W minus 2W squared. Okay, so that's step 3. Now we have area in terms of one variable W. So now we're going to take the derivative to find the critical point where you're going to have a maximum or minimum. Okay, so step 4 is take the derivative and solve for the variable. Take the derivative, okay, and equal it to 0 to get that critical point, and find or solve, not find, solve for the variable. Okay, so that's a critical point that we're going to do. So A prime equals 1,200 W. Sorry, I forgot to do this, right? Okay, it's 1,200 W minus 2W squared. So the derivative of 1,200 W is equal to 1,200. And the derivative of this is negative 4W. Okay, so now we set this to 0 and solve. So we can take this over, 1,200 negative equals negative 4W, and we get W equals 300. Okay, and that's our width. Now find length. Step 5. Answer. Or 5. Okay, so length was equal to 1200 minus 2 W's. So 1200 minus 2 times 300 equals 600. So our dimensions were 600 feet by 300 feet. Okay, I think we use feet there. So the length was 600 and the width was 300. So that means we had square feet for our pen. And here's our dimensions. Okay, so that's basically what you do. Is step 1, again, draw your diagram. Okay, write the perimeter equation. Use that perimeter equation to solve for one of the variables. Plug it back into the area equation. Once you have the area equation, take the derivative and set it to 0 and solve. That's called a critical point, right? And that's going to be either at a max or min. And then calculate what your maximum or what your dimensions would be. So that's our first example that we did. Very simple. Now let's do one with the odd shape. Okay, so sorry, I just had to answer that text. Let's do the next one here with an odd shape like that one problem with a crooked wall. So let's do a crooked wall one. Okay, so example 2 here. More area and perimeter. I guess I should have said B because I used A in the first one, but more area and perimeter with a different shape. So let's say we have 170 feet of planks to make a pen. Use the diagram to find the max area and the dimensions of the pen. So let me just pause this here. I'm going to answer this. Okay, so continuing on, we're going to do this type of problem. So again, we have the same idea of using the perimeter to calculate one of the variables in terms of the other, plugging it into the area, and then finding the dimensions of the pen. But this is going to be a little bit different because the red fence is what we're interested about. That's the 170 feet of wire that are planks in this case that we're using. Okay, so let's define this as our width by our length. So we still want the width and the length. Okay, so we've got a whole W here, a whole W or a whole L here. What's left here? This is basically W. This area is W minus 10 because it's W, but it's not this 10 feet of the wall. So this is W minus 10. Okay, so that perimeter that we're trying to figure out is only the red part. So step 1 is to write our perimeter equation for the 170 feet. So 170 equals W plus L plus W plus 10, or minus 10, pardon me. W plus L plus W minus 10. Oop, not 10. W minus 10. Okay, so if we collect the terms, 170 equals 2W plus L minus 10, add 10 to both sides, 180 equals 2W plus L. That's our equation for that. Now, because of the 2, I'm going to solve for L again. So L is equal to, subtracting 2 on both sides, 180 minus 2W. So there we have our equation of perimeter, writing L in terms of W. So we're going to maximize area again. So our area equation, is L times W. and we're going to plug this in for L. So our area is equal to 180 minus 2W times W. Okay, there's our L and there's our W. So we've got area is equal to 180 W minus 2W squared. Okay, so if I'm going to do that particular equation, I have to take the derivative to get a critical point where a maximum or a minimum could occur. So we're going to go A prime equals 180. Okay, so that's derivative of that minus 4W. Okay, so 0, if we set that, 180 minus 4W, and we're going to get 180 negative equals negative 4W. Divide by negative 4, and W in this case is equal to, what is that, 45, I think. 180 divided by 4 is 45, yes. So 45 is our W. Feet. Okay, and L is going to equal 180 minus 2 times 45, which in this case equals 90 feet. So therefore we have our dimensions at 45 feet by 90 feet. Okay, and that's only with 170 feet of fence available because the wall takes up all that extra space there. So if we do 45 by 90, what is the dimension of our pen? 45 times 90, the pen dimension is 4,050 square feet. Okay, so that gives us the dimension of our pen. So there's very similar to the first one. There's two area ones. Okay, and lots of rectangle pen ones there on the practice. And our third and final example that we're going to do today is another common one where you have some printed material that you're putting on a poster and you want to leave a margin around the edge. Now, be aware that when you're talking margins don't have to be equivalent all the way around. Top and bottom can be different. Left and right can be different. Top can be different than bottom. So when you're drawing your diagram, make sure you keep that into play. Okay, so again, let's do our third and final example for today. Let me just check my. Okay, sorry about that. Okay, our final one we're going to do is some printed material one. So pop this in here. Okay, so we want a poster. We want to print a poster with 90 square inches of printed material and a margin on the top and bottom of 2 inches, and the side margins will be 1.5 inches. Find the dimensions of the page that uses the least amount of paper. Okay, so what we're doing is we're minimizing the amount of paper that we're going to use. So we're going to be doing a min problem this time. And sometimes these printed poster problems can have a margin on the top, say, of 1 inch and the bottom of 3 inches. So keep that in mind when you're doing your drawings. Okay, so the first thing we should do when we're doing this, and I'll let you get that down, first thing we have to do is to take the derivative of this particular, draw the diagram, pardon me. We're going to take the derivative, but not first, because we don't have an equation even. We're going to do a drawing. So I'm going to draw the page out here. I'll use the square tool here. Okay, there's my poster, and in the middle here, I've got my written material or pictures or whatever, and I want to leave that's not very good. Let's get that a little more. Okay, and I've got it so that I want to leave a margin on the bottom and the top that's a little bit bigger than the bottom. So that's kind of how it's going to look. So this margin here, we know that first of all, if I take my marker here, that this is 90 inches squared. And we can say that this is some width by some height. Now we can also put it out on the paper here as well. So there's two ways to do this. You can label these two and W and H and then add, or you can label the outside and subtract. So both will work. I usually label the inside like that. So that if this is some height, we know that from the page, step one is that W times H is equal to 90 inches squared. Okay? And what we're trying to find here, and that's the width and the height of the printed material. But what we're trying to find here is the page. So if we know that this margin is 1.5 inches and that this margin is 1.5 inches and that this margin is 2 and that this margin is 2, we can then figure this out. So this whole page from here to here, the height plus 4 is all of this, and then the width here is W plus 3, because 1.5 plus 1.5 is 3. So this whole thing, we'll do it on the bottom here. So your page dimensions are there. So we know this, and that's going to help us give us W in terms of H or H in terms of W. So step one, draw it. Step two, write one variable in terms of the other. Okay, so it's no perimeter this time, so it's an area. So this would be, let's write, the way I did it here is I wrote H in terms of W. So H is equal to 90 divided by W. Okay, and then step three, write the area equation for the page. Okay, so writing the area equation for the page. So the area of that page is equal to H plus 4 times W plus 3. Okay, now let's plug it in. It has to be in terms of one variable, so we got to plug this 90 over W in where the H is. 90 over W plus 4 times W plus 3. Okay, now we're going to expand this out so that we can get the derivative somehow. Okay, so we don't want to do the product rule if we don't have to. Let's expand this out and use the power rule. It's a little easier. So area, okay, 90 times W divided by W is 90. 90 over W times 3 is 270 over W. Four times W is 4W. And 4 times 3 is 12. Simplify. 102 plus 270 over W plus 4w. Okay, now we're going to rewrite this in exponential form rather than over w. We'll have it to the -1 so that we can use the power rule instead of the quotient rule. So step 4, find the derivative and solve. Okay, so in this case, we're going to make some more space here for ourselves. And we're going to rewrite this equation. Area equals 102 plus 270 w to the -1, because that's that way we can use the power rule, plus 4w. Okay, so let's get a prime here. A prime, derivative of this, no w involved, so it's 0. Derivative of this is -270 w to the -2, and derivative of this is plus 4. Okay, so that is going to move the negative. Let's set it to 0. Set the derivative to 0. We're going to add the 0 plus the 4, get rid of that 0. Set this to 0. So -270 w squared, w to the -2. Sorry, w to the -2 plus 4. Okay, bringing the 4 over. -4 equals -270 w to the -2. Now, how do you solve for w here? So first thing we're going to do is we're going to now take this and we're going to write it back into the fractional form so that we can do cross multiplication here to solve it. -4 equals -270 over w squared. So now we don't have any negative exponents. So now we can cross multiply by going these two times that one. This will be like -4 over 1. So we solve, we go -4w squared equals -270. Okay, so now when we do it, we divide -4 on both sides. -4 into -270. I'm not sure, I think that's about 67.5, but let's check. Certainly is. Okay, and then we take the square root. So this will be plus or minus. Okay, and we'll round it off. Where's my square root? There it is. Okay, so that gives me 8.2 for the width of that page. Remember, that's the width of the printed area, not the whole page. The width is, and you got to add the margins. Okay, now that's for W. That was the width of the printed area. I guess I should have defined that W was the width of the printed area and so forth, but we drew a diagram, so that's good. And so now it could be plus or minus. Minus makes no sense, so that therefore the width has to be equal to plus 8.2 because we can't have a negative width of a page. Okay, and then we find L, so L, or the height, not L. Sorry, we called it H for height. Now we find the height. Okay, so we found that the height was 90 divided by W, right? This one way up here. So now we find H equals 90 divided by W, which is 90 divided by 8.2. Okay, it's rounded off a little bit. So when we do that, we're going to get the height of that page. 90 divided by 8.2. 10.97 or 11. Okay, so if we take 11 times 8.2, we should get about 90. a little bit more because of rounding. So the final step, step 5, is to answer the question. And we notice that if we look at our diagram back up here, we have to add 4 to the height and 3 to the width to get the dimensions of the page. So step 5, answer. Okay, so the total height of page is h plus 4, which equals 11 plus 4, which is 15 inches. And the total width of the page or poster is W plus 3, which was 8.2 plus 3, which equals 11.2 inches. So our page dimensions is 15 by 11.2, and our area of that total would be whatever that is, 15 times 11.2, which is 168 square inches. Okay, so that is our 3 examples, and that gets us into about 32 minutes or so, which should be enough for today. I'm not going to leave any practice today because tomorrow we'll do an example of volume type problems and also maybe a number problem in there or two. And then that would lead us into our day 3 as just being a practice on these type of problems before we get into related rates. Okay, so that's my stopping point for today, about 32 minutes. 3 different types of area problems. Now, keep in mind that when you're doing the problems on the book, keep in mind that you can have different margins and things like that, so be careful with your diagrams. All right, good luck. Like I said, no practice for today. It'll come after we do the volume stuff.